So moving on to the next behavioral pattern, let's talk about the state pattern. So some objects can change into many different states. So for example, a human being, if you think about a human being as an instance of a human being class, for example, so you can have different states. You can be on a happy state, you can be on a sad state, you can be on a tired state, for example. And if different objects' behavior, there should be an apostrophe there, is dependent on its current state, it would require bulky and annoying if else blocks to handle its dynamic behavior. So, for example, you as a human being could have different behavior when you're happy, different behavior when you're sad, different behavior when you're tired. So, meaning you have behavior that is dependent on your current state. The way you talk is different when you're happy compared to the way you talk when you're sad. So if you implement these behaviors, you have to write bulky if else clauses. If human dot is happy, for example, you have to check that. Then, like that, talk like a happy person. Else, if human is sad, for example, that is its state, then its behavior is different. Talk like a sad person, and so on. So you have to implement these bulky and annoying if else clauses where if there are new states, you have to add another else if clause. If there's a difference in the way you act for a specific state, then you have to change this specific part right here. So it's annoying. It's annoying to to handle dynamic behavior like this one. So, of course, the solution to this is the design pattern that we're going to talk about today, which is the state pattern. So, an object that can have many states, by the way, the state I'm talking about is different from the program state, by the way. This is like the general state. Uh, it is an overloaded term, actually, the term state in computer science. But anyway, I think you understood with the example I gave a while ago. So, an object can have many states. An object that can have many states should contain an attribute representing its state. So, what this design pattern does is it creates this new member, new attribute for your object. It has a state as a member. So instead of performing state dependent behavior directly inside the object, so instead of human directly performing the behavior talking, for example, you delegate this responsibility to its embedded state instead. So you have a state right here, which is of type state, and it could be happy, for example, it could be sad, etc. So when your human talks, what you do instead inside the body of the talking method, for example, you delegate that behavior, meaning you tell state instead to do the talking for you. So happy has its own way of talking, sad has its own way of talking, and etc. In this way, the object will behave according to its current state, which is what you're trying to do, making the object behavior dependent on its state. So what does the class diagram for this one look like? So you have here uh, an abstraction called state right here, which represents whatever state your object might currently be in. So it has context-related methods right here, two of them. You have context-related method and another context-related method, and it also has a state name right there. So these are the abstract methods for your state abstraction, which will then be realized by all of the possible states your objects could have. So for example, this specific context object right here could have two different states, initial state and another state. And if you notice right here, the relationship between your context and your state right here is a two-way relationship. So first, context owns an instance of state. So this is a composition relationship. So it needs a reference, it needs that reference to the state so that it can delegate its behavior. And at the same time, state uses a reference to the context that owns it, because it needs to be able to change its state whenever needed. So you need this instance right here, this relationship, this aggregation relationship from state to context, if state needs to control some of context's behavior. And sometimes you need to control its behavior when you're changing its state. You'll see this in an example that I will show you right here. So the state may be required to contain back references to the context object. That is what I'm talking about in this relationship right here. We call this a back reference to the one that owns it. So this is only required again if state methods required to access or control the context that owns it. And for the example that I'm showing you, it will need to control it because it needs to change its state. So I don't know if you're familiar of this diagram right here. This is a state diagram. If you're not familiar of this, you'll be familiar of this when you have ComSci 141 automata. So the way you interpret this is that you start with this initialization right here, and the object starts at an initial state. When you call another method, it will stay in initial state. But when you call method, it will go to another state. And while you're on another state, when you call another method, you will go back to initial state. But when you call method again while you're in another state, you will go back to another state, Japan. This is a diagram that represents how states are changing every time you're performing these behaviors right here. Also, by the way, I forgot to mention this part right here. When you are inside these context methods right here, current state, method and another method, for example, you have here a method and another method. Instead of actually performing the specific behavior for that context, if these methods are state related or state dependent methods, the way they're performed are dependent on state. So you delegate the responsibility to the embedded state or to current state right here, which is the name of your state instance. And for example, when you call method, what you do inside method is simply to call context related method for the current state. So current state dot context related method, you call this. For another method, you call where was that? Another context related method right here. You call this one instead. Okay, so let's demo what this looks like in code. And I think it's right here. So again, you have here the most important part. You have a state abstraction that contains whatever methods are dependent on state. So you have these two methods which are dependent on state. It also has state name right here. So the realizations for state, one of it is initial state. So we have here an init function that initializes the context or the object that owns this state, the back reference for the owner of this state. So you set that right here. Self dot underscore underscore context becomes the context that you pass in the constructor right there. I'm cluttering the code right here. Self dot underscore underscore context becomes the context that you pass right there. So here are the specific things that you do inside context related method. So you just print some print right here, some string. So manipulating the context on initial state, blah, 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 and then changing to another state. I should have named this a manipulator anyway. That's fine. So what you're doing here is just to differentiate the context-related method from another context-related method. So you have these two different prints right here. And according to our state diagram, so when you are in initial state, when you call the method, you go to another state. You change from initial state to another state. But if you are on initial state, but you call another method, then you stay in initial state. So you see that reflected right here. So context-related method, which will be called inside method for your context class, will change the state of the context. And this is the reason why we need that back reference, because we need to control context state. So you notice right here, we change the state right here. We call this context method called change state and pass a new instance of another state, thus changing the state of your context to a different state. On the other hand, another context related method, this one right here, which is called inside your another method of your context class, since it doesn't change the state, since according to this one right here, another method doesn't change the state when you're in initial state. Therefore, you don't do anything else after printing this string right here. And finally, you have this state name right here, which represents its initial, its name lang in string. I could also actually have named this the underscore underscore str function if I wanted to, just to make it stringable or printable, because I've already talked about this in the strategy pattern. But anyway, it's fine. You can do this as well to print it. Just call state name. So another state is another realization for state. It also has a reference to your context right here, right there. And when you are in another state, when you are calling method right there, you do not change into another state. You stay in another state. So you stay there, meaning there's no change states inside this call right here. On the other hand, if you call another method, then you print something and then change to initial state. You go back to initial state as reflected by this line right here, which controls the context reference by changing the state into a new instance of initial state. Finally, this is your context class right here. And you'll notice right here, when your context class is spawned, it starts with a state as initial state. And it needs to start with a certain state so that your methods will not return an error. If you do not initialize it with a certain state, then Python will complain saying that current state is currently null. So current state starts with initial state. And this is what I'm talking about when I say that the methods right here just delegate it to the state. Oh, that's not it. So now I'm what I should be pointing it to. So current state right here is doing the actual behavior. So when you call method, you're just delegating that to the state inside that context. So you're calling current state dot context related method. When you're calling another method, you're also doing the same. So you're delegating that to current state, but you're calling another context related method instead. This is the delegation part. So you have to do this because the behaviors method and another method are dependent on the current state of your context. So the state must be the one responsible for doing that behavior. And finally, it has a way of displaying the context itself. It just displays its current state. So to demo right here what I'm actually doing, let's look at this one. Let's give some space for it. So let's call this, I think this is called general example.py. So you start by creating an instance of context where the name is this. Actually forgot something right here. Let me write some more code because I forgot to display the name. It has a name, but I'm not using it. Let's concatenate that right here. Self dot underscore underscore. I think it is called attribute, attr. There you go. Let's remove the clutter and rerun general example. Whoops, that's an error. Oh, I'm actually not using it. Yikes. Let me remove this na lang. That's useless. Remove that. So meaning we don't need this anymore since we're only passing the self for the initialization right there. I think that's an artifact of the previous version of this Python file. There you go. That's the correct one. So again, tracing our code right here, we start by creating a new instance of context, as you can see right here. So displaying what that context currently is, you see this one right here. Current state, initial state. So when you call method right here, c.method, since your state is currently an initial state, it will perform this behavior right here, and then after that, it will change it to another state. That's because according to the state diagram, if you're in initial state and you call method, you change from initial state to another state. After that, we call another method performing this behavior right here, and then changing back to initial state right there. And then calling method again will perform this behavior and then change back to another state. But when you call method again while you're still in initial state, or sorry, while you are on another state, sorry, you are already in another state, when you call this method again, this one, then what's going to happen is it will perform this behavior, but there are no changes in state because you are already in another state. So by doing all of this, the behavior of your context is now dependent on its current state. So there you go. So just to display what the final state of your context is after all of these methods and changes to state, let's display our context after all of that. Let's add another space right here, another new line that looks neater. And that's an error because I misspelled display. So the final state for your context is, of course, another state. You see that right there. So there are no changes from another state to another state because you're using the method c.method. There you go. There you go. So the example that you're going to be implementing for your lab exercise is this states of matter model right here. So the state of any given matter is dependent on the pressure and temperature of its environment. So if you heat up some liquid enough, it will turn to gas. If you compress it enough, it will become solid. So you are to build a less sophisticated version of this model in code. Matter comes in three states. Actually, there are more, but for this specific context, let's just concern ourselves with these three states right here: solid, liquid, and gas. So the state of the matter may change if you put or remove pressure on it or you heat/cool it. So the state diagram of matter would look something like this. So it will initially start as liquid state because I think the most ubiquitous form of matter I can think of is water, man. So water starts liquid state in room temperature and atmospheric pressure. So for this example, this nondescript matter right here will also start in liquid state. So again, if you cool or compress this liquid right here, it will change to solid state. If you compress or cool this solid state right here, it will stay in solid state. But if you heat or release its pressure, it will go back to liquid state. Uh, while it's in liquid state, if you heat or release its pressure, it will go to gaseous state. If you heat or release this gaseous state again, it will stay in gaseous state. But if you cool or compress it, it will go back to liquid state. So to implement something like this, you would need to create matter which owns an attribute state, which represents the matter's current state. Since there are three states, you create three realizations to a common abstraction to state. So before we move on to what the UML for that looks like, let's look at how your code looks so far. So right now you currently have matter right here, and it has a name and it has a current state. So right now, since you haven't implemented, you haven't created the class state yet, I have added it here, none. So you need to change this to the appropriate initial state, which is liquid state. So that will be up to you. So changing state right here, I have written pass for this one. You need to put actual implementation inside these once you complete the code, once you complete all of the classes. And what I did right here for matter, I added a string representation right here to make it stringable and printable. So this is another instance of formatting strings. Actually, you've never seen formatting strings with more than one argument. So you have two arguments right here, two strings, self.name and self.__name. So if you have two arguments, the left operand of your percent operator right here, you just put a parenthesis, you just put this tuple right here, self.name comma self.state. So self.name will be concatenated inside the first %s, and self.__state will be concatenated in the second %s. So this is just your formatted strings lang gyapon, but you now have more than one concatenation occurring inside there. So that's what your current lab exercise looks like. So you need to implement all of the matter states, and you need to create the state abstraction as well. And that's up to you to complete that now. Okay, so going back. So when you compress/release/cool/heat the matter, you delegate the appropriate behavior and state changes inside state's version of that. So inside here, you don't actually perform specific behavior, right? You just delegate to the state inside this matter right here, to this attribute right there. When you call change, oh, that's not it. Not change state, by the way, compress. So when you call compress, for example, you just call state's version of compress. When you call release, you just perform state's version of release, and so on. You also have to place here a way for matter to change state. So when you change state, you just call whatever matter that is m.change_state, and then pass the new state for that. And you have to write the actual implementation of that method right there. There's an example of that in this general example right here. Changing state is just as simple as this. Current state becomes next state, which is passed right there. So yeah, you need to create three realizations for state for the different states of matter: solid, liquid, and gas. And here's more information on what I mean when I say you delegate the behavior. So this is what the class diagram for that looks like. So you have solid state, liquid state, and gaseous state as realizations for your state abstraction. It has the same name. So compress, release, heat, and cool. It has the same name as the context or the matter methods: compress, release, heat, and cool as well. So these functions have the same name, but what they do is they basically call state's own methods of compress, release, heat, and cool. And again, matter owns state right here. It owns that, but it also has, state also has a back reference to matter that you can see right here. It needs that back reference because the state whatever it is, whatever realization it is, it needs to change its state from solid to liquid, from gas to liquid, for example. It needs to do that. It needs to control and access matter right here. So you'll notice that in this specific attribute for each of the state realization matter. So matter owns an instance of state, and that instance has an attribute called matter. The attribute matter is the reference to the instance of matter that owns it. The state instance needs this reference so that it can change the matter's state when it is compressed, released, heated, or cooled. And you just follow the state diagram right here on what will happen. So when it's in liquid state and you cool, compress, solid state, blah, 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 etc. Just follow the state diagram right there. So just to demo what a working solution for that, what it should look like, let me just display. It's a spoiler on what you'll be coding. Let me just demo what this does when it's completed. Let's clear all the clutter. Python state solution.py. There you go. Oops. So just to trace what's going on right here. So matter, which is called water right here, that's its name. It's instantiated as a liquid. So when you print water without changing its state, so its initial state is it's a liquid. And if you notice right here, print water will automatically work because matter has already been printable through the __str function, as I've shown you a while ago. And when you compress water right here, it will print something like freezing. That's up to you what you're going to print right here. And printing water again, you'll notice that the state has changed into solid. Then when you heat water right here, it will print melting. And after that, you print water again, you'll notice that the state has changed into liquid again. If you call water.release, it will print evaporating, and printing water again, you'll notice that the state has changed into gas. Heating it while it's still in gaseous form, right there, it will print heating. And then if you print water again, you'll notice that there is no change in state because heating a gas, it will still become gas. But when you call water.cool, it will display condensing. And if you print the final state of your water right here, I forgot to do that. Let me add that line right there. Oops. Water. Oops, not that. I mean print water. I don't want a new line. So printing everything again, the last or the final state for water is liquid since you have cooled it from gas. Great. So your finished product or your finished code should work similar to what you're seeing right now. So you can try and test it by yourselves, and it should perform this behavior that I'm showing to you. So why is this pattern elegant? So single responsibility principle, one of solid design principles, behavior related state is delegated to the state itself. So the state is now the one responsible for performing behavior related state. Or sorry, state related behavior. Because the behavior for water or the behavior for matter is dependent on state, the one responsible for implementing that behavior, for performing that behavior, should be state itself. It also adheres to open-close principle. You can incorporate new states to the system without touching any existing client code. So for example, if there are new states here, There's a supercritical state, for example. You can easily introduce that new state by creating a new realization to your state abstraction right there, and just do similar things right here. Implement all of the abstract methods and etc. So it is easy to incorporate those kinds of changes. It is very maintainable. And then finally, this is elegant because implementing this pattern will remove those bulky and annoying state conditionals that you need to do. Those if-else checks. You don't have to check if matter is currently liquid, if matter is currently solid, etc. You don't have those checks anymore because the responsibility for performing behavior is again delegated to the state inside matter. And that's it for state. Here are the instructions. Here are loose instructions on how do you implement state in general. And that's it. Thanks, y'all.